Hello student, today I am giving my lecture on paper number 13, Functional Analysis 2, Theorem. State the complex Stone-Weierstrass theorem. Let X be a compact Hausdorff space and let A be a closed subalgebra of script C of X, C, which separates points contain a non-zero constant function and contains the conjugate of each of its functions, then A is equal to C. We have given X is compact Hausdorff space and A is closed subalgebra of script C of X, C, which separates the points contains a non-zero constant function and contains the conjugate of each of its function, then A is equal to script C of X, C. Theorem. Next theorem. If A is self-adjoint, then A cap is dense in script C of script M. We know that A cap is a subalgebra of script C of script M, which separate the points of script M and contains the identity function. Hence, A cap conjugate is a closed subalgebra of script C of script M, which separate points of script M and contains the identity function and also contain conjugate of each of its function. So, by above theorem, complex Stone-Weierstrass theorem, A cap closure is equal to script C of script M. So, A cap is dense in script C of script M. The next theorem, if A is self-adjoint and if norm x square is equal to norm x whole square for every x belongs to A, then the Gelfand mapping x to x cap is an isometric isomorphism of A onto script C of script M. Proof: we have norm x square is equal to norm x whole square if and only if norm x cap is equal to norm x, and the mapping x to x cap x to x cap is an isometric is an isomorphism from A onto A cap, and since mod norm x is equal to norm x cap and a function x to x cap is an isometric isomorphism of A onto A cap onto A cap, and so A cap is closed because A cap is image of whole space A. So A cap is equal to A cap conjugate is equal to script C of script M. Hence, the Gelfand mapping x to x cap is an isometric isomorphism of A onto script C of script M. Now, we see the definition of Banach star algebra. Let us see a Banach algebra A is called Banach star algebra if it has an involution, that is, there exists a mapping x to x star from A into itself with the following four properties. Following four properties satisfy, then it's called Banach star algebra. X plus y star is equal to x star plus y star. Alpha x star is equal to alpha conjugate x star. X plus y star is equal to y star into x star. X star star is equal to x star star is equal to itself. This notation is adjoint of x. This is notation of adjoint of x. Now function x to x star is 1 1. So let we let x star is equal to y star implies x star star is equal to y star star. By using this property, x star star is equal to x. So x star star is equal to x and y star star is equal to y. So x is equal to y. We take x star is equal to y star implies x is equal to y. So the function is 1 1. Now second, adjoint of 0 is equal to 0. So x 0 plus x star is equal to 0, x star is equal to 0 plus x star is equal to x, 0 star plus x star. So we cancel out this. 0 is equal to 0 star. Now third, 1 star is equal to 1. So 1 star is equal to 1 into 1 star is equal to, we can write 1 is equal to 1 star star. So this is equal to 1 into 1 star star is equal to 1 into 1 star is equal to 1 star star is equal to 1. So 1 star is equal to 1. So adjoint of 1 is equal to 1. Not x star is equal to is called the adjoint of x. Now we see the definition of self-adjoint. Let us see the definition. A subalgebra of A is said to be self-adjoint if it contains the adjoint of each of its elements. It contains the adjoint of each of its elements. For example, A is Banach star algebra and A dash is subset of A, then A dash is subalgebra. For for every x belongs to A dash implies x star belongs to A dash, then A dash is self-adjoint. Now we see the next definition, star isomorphism. Uh, so let A and A dash be Banach star algebra. An isomorphism f from A to A dash is called a star isomorphism if f of x star is equal to f of x star. This is definition of star isomorphism, and isomorphism function from defined from A to A dash is called star isomorphism if f of x star is equal to f of x star. Now we see the lemma statement. If norm x star is equal to norm x, then involution is continuous. Let us we see the proof of the lemma. Suppose xn tends to a, sorry, xn tends to x in A. So let norm xn star minus x star is equal to norm xn minus x star is equal to norm xn minus x, because using this we can write this is both are equal, but xn tends to x, so xn minus x tends to 0 as n tends to infinite, so this tends to 0, so xn star tends to x star, so the involution is continuous. Now definition: B star algebra. A Banach star algebra A is said to be B star algebra if norm x star x is equal to norm x whole square for every x belongs to A. For example, complex number is a Banach algebra. We define f we define z star is equal to z conjugate, and mod z star into z is equal to mod z conjugate into z, but z conjugate into z is equal to mod z no mod z square, hence C is B star algebra. Now next lemma: let A be B star algebra, then norm x star is equal to x. So we see the proof. Let A be a B star algebra. So norm x square is equal to norm x star x, and it is less than or equal to norm x into norm x. So we cancel out norm x. So norm x is less than or equal to norm x star for every x belongs to A. Equation number 1. For x star belongs to A, here we use x star belongs to A by 1. By equation 1 we can write norm x star is less than or equal to norm x star star, but x star star is equal to x. So norm x star is less than or equal to norm x. Equation number 2. From 1 and 2, from result 1 and 2, we get norm x star is equal to norm x. Hence the proof. Here given the two example, let x be a topological space, then script C of x is a B star algebra relative to the involution defined by f star x is equal to f of x conjugate. Second, if H is a non-trivial Hilbert space, then script B of H is a B star algebra with the adjoint operation T to T star taken as the involution. Now let us see the definition of normal, self-adjoint, and projection. So uh, let A be a let A be a Banach star algebra. Let x belongs to A. Then first, x is said to be normal if x star x is equal to x into x star. Second definition, self-adjoint. If x is said to be self-adjoint if x star is equal to x, and X is said to be projection if x star is equal to x and x square is equal to x. Now the theorem, if x is normal element of B star algebra A, then norm x square is equal to norm x whole square. So proof, norm x square is equal to norm x into x. So it is less than or equal to norm x into norm x. So this is equal to norm x square. So we let norm x square is less than or equal to norm x whole square. Result number 1. Now norm x star square into norm x square is equal to norm x star into norm x whole square, because this star algebra norm x star is equal to norm x and norm x star x is equal to norm x square. So we can write into 2 times norm x into norm x. So using this, norm x is equal to norm x star. So norm x star into norm x is equal to this and all square. So this is equal to norm x star into x star into x, because norm x square is equal to norm x star into x. Using x into y star is equal to y star into x. So x star into x, because x star is equal to this is x and this is y. So x star into y star into x star. So x star into x star star is equal to x. Now here x star into x star using associative property, but here we have given x is normal, so x into x star is equal to x star into x. So x star into x star is equal to x star square into x is equal to x square. So this is less than or equal to norm x star square into norm x square is equal to norm x star into norm x square, and this is less than or equal to norm x star whole square into norm x square. Here we cancel out norm x star square and norm x star square, so we get norm x square is less than or equal to norm x square, equation number 2. From 1 and 2, from result 1 and 2, we get norm x square is equal to norm x whole square. Now we see the theorem, the Gelfand-Newmark representation theorem. Statement: if A is commutative B star algebra, then the Gelfand mapping x to x cap is an isometric star isomorphism of A onto the commutative B star algebra script C of script M. Now see the proof of the theorem. Here A is commutative, so for every x belongs to A is normal, then so norm x square is equal to norm x whole square. So it remains to prove that A is self-adjoint. So to prove this, we shall show that for every x belongs to A, there exists y is equal to x star such that x star cap of m is equal to x cap of m conjugate for every m belongs to script m. Now, so claim is if x is self-adjoint, then x cap of m is real for every m. Suppose x cap of m is equal to alpha plus iota beta and beta not equal to 0. Here we consider the complex number alpha plus iota beta for some m belongs to m. So let y is equal to x minus alpha into 1 upon beta. So now we are applying adjoint y star is equal to x minus alpha into 1 upon beta star. So x star minus alpha conjugate is equal to alpha upon beta conjugate is equal to beta. Alpha and beta both are real. Here x is self-adjoint. Here x is self-adjoint. So x star is equal to x. So we get x minus alpha into 1 upon beta. This is equal to y. Here we get y star is equal to y. So y is self-adjoint. Now y cap of m is equal to x cap of m minus alpha into 1 cap of m upon beta. But x cap of m is equal to alpha plus iota beta minus alpha into 1 upon beta. So alpha alpha cancel out. So I beta upon beta. So beta beta cancel out. So is equal to I. So y cap of m is equal to I. Now y minus iota into 1 cap of m is equal to y cap of m minus I into 1 cap of m. 1 cap of m is equal to 1. Y cap of m is equal to I from here. So 1 minus I minus I is equal to 0. So this is equal to 0. So y minus I into 1 belongs to m because x cap of m is equal to 0 if and only x belongs to m. Let m star is equal to m star where x belongs to m. Since x2 x star is 1 1 and on 2, so m star is a maximal ideal of A. So it contains y minus I into 1 star is equal to y plus iota into 1. So y cap of m star is equal to minus I because reason is here. If k is any positive real number, then y minus I k conjugate of m star is equal to y cap of m star minus I into k. Y cap of m star is equal to minus I. So minus I into k. Now minus I is common out. So minus I into 1 plus k. So we apply no mod. So mod minus I into 1 plus k is equal to mod y minus ik into 1 cap of m star. But mod x of m is less than or equal to norm x. So this is less than or equal to norm y minus ik cap into 1 and also norm x cap is less than or equal to norm x. So this is less than or equal to norm y minus ik into 1. Similarly, 1 plus k is less than or equal to norm y plus ik into 1. Now 1 plus k square is equal to, we can write 2 times. So we put the value 1 plus k is equal to this, and 1 plus k is equal to this. So it is less than or equal to y minus ik into 1 into y plus ik into 1 is equal to, we can write y minus ik into 1 is equal to y plus ik into 1 star adjoint, because y minus ik into 1 is equal to y star plus I conjugate k into 1, because here y is self adjoint, and this is equal to y plus ik into 1 star, and is equal to norm y plus ik star into y plus ik, because A is B star algebra implies norm x star is equal to x, and norm x star into norm x is equal to norm x star into x. So this is equal to, this, both are equal. So y minus y plus ik into 1 star is equal to y minus ik into 1 into y plus ik into 1, and simplifying this is equal to norm y square plus k square into 1. It is less than or equal to norm y square plus k square. So 1 plus k square is less than or equal to norm y square plus k square. Simplifying this, 1 plus 2k expansion of this 1 plus 2k plus k square less than or equal to norm y square plus k square. So k square cancel out, 1 plus 2k is less than or equal to norm y square. Since k is an arbitrary positive real number, then equality is not possible, because take k is equal to norm y square, both this is greater than this, so here we get contradiction to b not equal to 0, so our assumption is wrong. So we must have, if x is self-adjoint, then x cap of m is real for every m, and let y is equal to x plus x star upon 2 and z is equal to x minus x star upon 2i, then clearly y star is equal to y and z star is equal to z. Both are self-adjoint, and y plus iota z is equal to x. So x star cap of m is equal to, put the value of x, y plus iota z star, and now y plus iota z star is equal to y minus iota z, and now apply cap, y cap of m minus I, z cap of m, and here y cap of m and z cap of m both are real, because y and z are self adjoint, so this is both are real. So y cap of m conjugate is equal to y cap of m, so we can write y cap of m is equal to y cap of m conjugate minus I into z cap of m conjugate. So we apply y cap of m plus I, z cap of m conjugate, and so y plus iz cap of m, and y plus iota z is equal to x, so x cap of m conjugate, hence the theorem. And thank you.